The chemist and Nobel laureate Paul Crutzen is well known for having coined the term Anthropocene in 2003, or at least for initiating the term's unhampered global success. Once confined to the spheres of academia, the term has, over the course of the last decade, become a familiar part of the global discourse on environmental change and humans' role in the ongoing climate crisis. But Crutzen didn't stop at formulating a concept to describe how humanity could now exert influence as a geological force, altering hemispherical material flows. Just 3 years later, in 2006, Crutzen published another small essay on the potential of implementing a technological solution to ongoing global warming: albedo enhancement by stratospheric sulfur injections. Now, the subtitle went on to claim that this might be a solution to our society's dilemma in climate policy, but the article also meant to break a taboo in suggesting that humans could inject stratospheric aerosols, preferably sulfur-based, with balloons or comparable technical measures into higher strata of the atmosphere to counteract anthropogenic climate change. The basic idea behind this is simple and yet fascinating. Large volcanic eruptions eject all kinds of dust and chemicals into the atmosphere, which reach even into the lower levels of the stratosphere, up to 10 kilometers or higher. Now, while the relatively heavy volcanic ash falls down within a few weeks, the lighter material remains in the highest parts of the troposphere or even the lower parts of the stratosphere. Sulfur dioxide in particular reacts here with water to form tiny droplets of sulfuric acid. And these very small droplets, or even solid particles called aerosols, get caught up in moving air and moving air masses and are thus transported around the globe. Now, we have all witnessed this phenomenon recently when burnt bioorganic mass from Californian forests was transported around the northern hemisphere. A thin yet effective aerosol layer, in the case of the volcanic eruptions, deflects a considerable fraction of solar radiation before it can reach the ground. Now, this NASA simulation here of different types of aerosols, salt particles in blue, fossil fuels in grayish-white, burnt organic material in green, and desert sands in orange, demonstrates how such aerosol flows are a constant part of geophysical dynamics on this planet. Even a minor volcanic eruption, like the one that happened in January 2007 in the Comoros between Madagascar and Africa, can result in a widespread dispersion of sulfate aerosols, here simulated in white, and across southern Africa. Now, this simulation of the 2007 eruption, which was just a very small event compared to the large sulfur events we have seen in the past, provides us with an impression of what much larger sulfur injections might have looked like in geophysical terms, and why they influence global climate for up to 3 years. After this time period, the last aerosol particles sink to the ground and no longer influence global or regional climate. The best known historical case study for such a volcanic event was the eruption of Mount Tambora in Indonesia in 1815, which caused global temperatures to plunge and precipitation to increase in 1816, and to a somewhat lesser extent in the years to follow. Now, this phenomenon has suggestively been described as the year without a summer, and as it is such a popular topic in the geosciences, it's reasonable to assume a Tambora-like situation also came to the mind of researchers when thinking about the mitigation of anthropogenic climate change. Crutzen's initiative from 2006 has initiated an ongoing public and scientific debate on the feasibility of using geoengineering to mitigate climate change. A global overview of research projects on this so-called solar radiation management reveals an obvious concentration of these projects in Anglophone countries like the US, the UK, and Australia. Of these 23 projects, only 7 proposed a controlled injection of sulfur dioxide into the stratosphere to cool ground temperatures in an attempt to mimic the natural cooling effects of a big volcanic eruption. Notably, only 3 of them actually conducted experiments on how to release sulfates, while the other 4 projects relied on climate modeling to simulate the effects of artificial aerosol injections. Other projects followed different paths of solar radiation management. Some preferred the injection of water droplets rather than sulfate aerosols, aiming to create brighter clouds that would deflect sunlight before it even reached the ground. Other approaches aimed to thin cirrus clouds to allow more heat to escape into space. And there are more ideas out there, like enhancing ocean surface albedo by adding stable, non-dispersive foam or microbubbles to the sea surface. And even more audacious studies explored ideas like clearing large areas of boreal forests in Russia to provoke a cooling effect, as snow-covered plains deflect sunlight more efficiently than snow-covered trees. So stratospheric aerosol injection is just a small fraction of current research on solar radiation management. And of course, a key concern is that it is not addressing the underlying increase in atmospheric greenhouse gases at all. In the political realm, it's also criticized for being influenced by lobbyists supported by big corporations like Shell or ExxonMobil, with an urgent and vital interest in technology-based fixes to anthropogenic global warming. There are further concerns and criticisms about the long-term governance of such aerosol injection projects and their possible weaponization. But I want to focus here on the climate-related uncertainties associated with stratospheric aerosol injection and its potential impact on human societies. First, climate models are crucial to understand both future and past climatic changes and the role of climate drivers like volcanic eruptions. And also to consider how artificial manipulation like the injection of sulfate aerosols might influence global, regional and local climates. Especially the finer scales down to regional and local weather impacts are hardly understood. Furthermore, climate reconstruction studies have focused on the changes in temperature after major volcanic eruptions, while paying far less attention to the impacts on global and regional precipitation. A lot depends on the region where the volcanic eruption takes place. High latitude eruptions in the northern hemisphere change precipitation, for example by weakening tropical monsoons, in a different way than tropical eruptions do. Sulfate aerosol injections might produce winners and losers, or at least a rather unevenly distributed modification of climatic conditions over several years. Now, this danger of uneven climate change has been clearly documented for 1816, the year without a summer. For while most of the continent of Europe faced severe cooling and continuous precipitation, Eastern Europe was hardly affected. Grain harvests failed in most parts of Europe, as this impressive memorial site within the Church of St. Michael in Schwäbisch Hall in southwest Germany demonstrates. 4 very small loaves of bread remember the famine year 1816, while the first wheat ears of the 1817 harvest were also preserved inside the church in this object that you can see here. But the summer temperatures were normal or even above average in Eastern Europe. Russian and Ukrainian grain producers profited from bountiful harvests that they sold to their starving neighbors at a considerable profit in 1816 and the following years. You see on the right side a reconstruction of temperature in the summer of 1816. Now, in fact, the rise of the port city of Odessa on the Black Sea has been associated with this economic success story for Eastern Europe after the Tambora eruption. Now, what is the role of medieval history in all that? It's worth to remember that the most influential explosive volcanic eruptions of the past 2 millennia, which you see here in a recent reconstruction, happened in the medieval period. First, a double eruption in the 6th century that probably triggered the so-called late antique Little Ice Age. Then, the eruption of the Samalas volcano in Indonesia in the mid-1250s. And finally, another yet unidentified eruption event in the mid-15th century, which was known as the Kubay eruption until research rightfully changed the validity of this identification. How do we know about these past volcanic eruptions? Without a single exception, and in stark contrast to the famous eruptions of the 19th century like Tambora or Krakatau, we do not have any written eyewitness accounts of medieval volcanic eruptions on a scale that could influence global climate. Narrative texts from the medieval period, originating from the area of modern Indonesia, do not provide concise chronologies, and other areas like pre-modern Melanesia did not produce written records, but relied on an oral tradition of genealogies that likewise does not provide reliable dating of reported events. Even if we had more detailed information about the dates of volcanic eruptions in the pre-modern period from written sources, we could hardly estimate their influence as climate drivers from such accounts. For such deduction requires information regarding the amount of sulfur injected into the atmosphere. Now, the key to determining the magnitude of the sulfuric injection caused by a specific eruption can be found in the polar ice shields. The aerosols of sulfuric acid come down in precipitation within 3 years at most of them already in the year after the eruption. The annual snowfall layers in polar regions, mainly Greenland and Antarctica, are compressed into layers of ice, each of them containing distinctive chemical and physical traces from Sahara dust to sulfuric acid. Scientists count these layers backwards and measure these traces, for example, sulfuric acidity, in each layer to create a chronology that provides us with a good record of past volcanic eruptions that injected large quantities of sulfur into the atmosphere and hence, most probably, influenced global climate. There are, however, some inherent dating problems with this method. So snowfall deposits, and thus the amount of sulfuric acid in one specific ice core, might vary from place to place. So the only reliable information comes from cross-referencing multiple ice cores to identify widespread sulfur peaks. Furthermore, researchers can't see the annual layers in ice cores that go back several hundred years. So they have to measure seasonal variations of dust and chemicals in these ice cores to identify annual layers. And eruption dates acquired with these methods may be off by 2 to 5 years. So it comes as no surprise that researchers looked for so-called stratigraphic markers, well-known volcanic events that should have left a considerable peak of sulfur in all ice cores. These events are used to synchronize peaks in different ice cores and validate their specific chronologies. Now, for the 19th century, the Krakatau or Tambora event are precisely dated and well documented in historical sources. But when it comes to the largest eruptions of the last 2 millennia, we have mentioned them before, the so-called Kubay event in the 15th century, Samalas in the mid-13th century, and the volcanic double event in the 6th century, historical evidence is much scarcer. And yet even more important. In 2005, Mike Bailey suggested that ice core chronologies were off by 7 years in their dating of the double eruption in the 6th century that triggered the so-called Little Ice Age. Now, this sparked a long discussion among scholars regarding these dates, but today both ice core researchers and dendrochronologists agree that these events happened in 536 and 540, years that have always been clearly confirmed by written historical sources, which geoscientists have too long neglected and underestimated. Now, this is not to suggest that written sources can always be taken at face value. There are potential pitfalls. Let me demonstrate this with regard to what is widely accepted as the largest volcanic event of the last 2 millennia. The Samalas Eruption that is now dated to 1257, or was once dated to 1258 or even 1259. A key argument for dating the event to 1257 was advanced by Sébastien Guillet in 2017, with reference to historical sources. First, he evaluated chronicles from the whole 13th century, European chronicles obviously, and counted the references to bad weather. And in his results, 1258 stood out in an astonishing way, as you can see it in the graph on the left side. And as we would expect after the most sulfur-rich eruption of the last 2 millennia. But there's a problem. While Guillet carefully collected all the relevant material from European chronicles for 1258, for the other years of the 13th century he relied on the important yet incomplete collection of Pierre Alexandre, which focused exclusively on the territories of modern France, Germany, the Benelux countries, northern Italy, parts of Spain and Poland. Alexandre's collection does not include the British Isles, but the bulk of information on bad weather in this decade comes from English chronicles. So excluding this body of sources is thus a clear misrepresentation of historical evidence. And my alternative count, which you can see on the right side, still shows a peak in 1258, but a period of extraordinarily bad weather sets in as early as 1256. Now, furthermore, Guillet's argument relied on a quote from a German chronicle that referred to the year 1258 as Munkeljahr, a really strange vernacular term, the meaning of which is very unclear. Guillet followed correctly the interpretation of the 19th century editors of this chronicle, who interpreted Munkeljahr to mean a year of fog and darkness, which could refer to the visual effects of an unusually dense aerosol layer in that year 1258. Now, with the Tambora eruption in mind and thinking of the year without a summer in 1816, this sounds very reasonable. However, a closer look at the quote in question reveals that the chronicler is not talking about weather or about the intensity of the sun, but rather about the low quality of food and especially wine. Etymological dictionaries of wine growing in Germany confirm that the verb munkeln means that the wine tastes moldy, which of course could be the result of the undisputed bad weather in 1258. But it's not referring to an aerosol layer. The key question here is whether or not the bad weather started before 1258, and whether we can find more convincing descriptions of a volcanic aerosol layer. In a recent publication, I argue that we can find these descriptions and probably should redate the eruptions to 1256 or even 1255. Now, what is the importance of all this for current discussions on geoengineering with solar radiation management? As we've seen before, modeling is a key feature to simulate the impact of past volcanic eruptions. And these climate models are based upon presumably precise data on eruption dates, sulfur injections, and subsequent temperature reduction. In the Samalas case, though, the drop in global temperatures of the northern hemisphere is not detectable before 1259. Now, if in fact there was a delay of 2 or even 3 years between an eruption and the related hemispherical cooling, this raises most serious doubts about the conventional wisdom on the effect of sulfur injections in the atmosphere. Now, we should remain very cautious about the predictive reliability of model simulation when the basic facts on the largest volcanic eruptions in the past, like dates, sulfur loads, and associated cooling, remain so unclearly connected. Let me give you another example from the Middle Ages. The second largest volcanic eruption has been identified, you may remember, in ice cores for the mid-15th century. It was long associated with the submarine caldera of Kuwait in Vanuatu and had been dated to 1452. Rather baseless speculation even connected it with major historical events, like the fall of Constantinople in 1453. Now, recent volcanological research has precluded the association of Kuwait with the mid-15th century event. Tree ring and ice core research have suggested that there might have been 2 eruptions in close temporal proximity, probably one around 1453 and another one, according to ice core analysis, in 1458. While tree ring research indicates a drop in temperature in 1466 and hence an eruption in 1465. My analysis of historical sources also points rather clearly to 1465. While the climatic impact of 1453 is less well documented in historical sources. Now, recently a publication has challenged the significance of the ice core sulfate peak in 1458, which might be linked to an eruption on Antarctica rather than a volcanic event with truly global impacts. Now, in a nutshell, the contradictory finding of ice core research, dendroclimatology, and historical research have not yet been resolved. In other words, for none of the 2 largest volcanic eruptions of the past 2 millennia do we have consolidated evidence on eruption dates and hence on the connection between temperature, precipitation, and volcanic aerosols. What we should expect is a smooth fit of historical descriptions and dendroclimatological data, as both of them are annually resolved. The ice core analysis still has to correct for its inherent dating uncertainties, and yet we need a reliable attribution of specific eruptions and their reconstructed sulfur injections into the atmosphere. The work of traditional medievalists with narrative sources is crucial in the determination of precise chronologies of past volcanic eruptions. Unless we can reasonably synchronize historical facts, ice core data, and tree ring reconstructions, we should not assume that we have understood the complex climatic processes that followed large volcanic eruptions in the past 2 millennia. Let me summarize and return to the best researched of all sulfur-rich volcanic eruptions of the past, Tambora. Now, a lot of cultural phenomena have been associated with the experience of the year without a summer in 1816. Many of these hypotheses are not very well founded. Yet, one deserves our attention. When a group of young English writers, both men and women, decided to stay in their houses in Switzerland on Lake Geneva because of this end-of-the-world weather they were facing daily in this gloomy summer of 1816. This included 130 days of rain between April and September 1816. One of them, 18-year-old Mary Godwin, better known by her later husband's family name as Mary Shelley, began drafting a story and that eventually entered the literary canon, Frankenstein, which is not a mere horror novel, but a parable for the modern age about how humans underestimate the risk of their technological ambitions, only to be chased and finally overwhelmed by a monster of their own creation. I hope I have demonstrated how medieval history might help us to re-evaluate epistemological uncertainties within the whole approach of solar radiation management via artificial aerosol injections. We, as a global society, would do very well to think very hard before we make solar radiation management the Frankenstein of the 21st century. Thank you.